One way of building new functions is considering inverse functions. So here is inverse functions. So what do we mean about inverse functions? So a function that assigns for each x, so imagine for each x a unique image, only possibility. For example, suppose that we have f correspondence like that to another function. Okay, let's do. Okay, so we are allowed to have then just a correspondence to a unique, unique point. Each element of the domain of f, we can assign a unique value. Okay, a unique distinct value. Okay, so here is the definition. So let's set the definition. So function. So we will say such function is called a one-to-one function. That f is one-to-one. Is one-to-one. If function. So we need a function. Property of function. If it never takes on the same value twice. Okay, that is each time you have two distinct images, whenever x1 is different from x2. Okay, so whenever x1 is different from x2. So if you have the equality, necessarily x1 is equal to x2. If you have x1 different from x2, then necessarily the images are distinct. Okay, so this is the definition of inverse function. Geometric way to identify visually that my graph of function is a graph of one-to-one function is to use the horizontal line test. Okay, so here it is. Like we did for function, we used the vertical line test. Here we have horizontal line test for the graph of function, for the graph of a function. Okay, so we have so we can, yes, the test sets that f is one-to-one, characterization is one-to-one, if and only if no horizontal line intersects its graph more than once. Okay, so we have, if you remember, so a function. So for example, this function, let's say this function, if on this interval, let's say it is a function because I can imagine a vertical line, each vertical line. Okay, if I graph imagine a vertical line and move it along the interval described. Okay, move this line. Then we check that the intersection each time is only one point. Okay, so this is the vertical vertical line test to check the purpose, check that f is a function. Now the new test we are telling about is an horizontal. We can imagine, let's imagine an horizontal line, okay, and we check and move it along the set of values taken by f on the image set, and we can move it along and check each time if the intersection is only one point. Then we will say that we have, and you see now if both are satisfied. So yes, we have for each x we have an only one y as an image, okay, each time. So that makes my function a one-to-one function. So now there is something notations. Yes, we need to know them, some notation. So because we have this correspondence for each time you assign to the range, imagine you set, so we stop at the range here, we describe the range of f here, we keep only these images, then I am able to define a new function is starting from these values to the domain. Okay, so I can imagine a relationship like that assign for each, if this is an x, this is a y, for each y a unique x. Okay, so I can define a new function like that, and this particular function, this is what we call the inverse function. Okay, so we call it the inverse function. So let's yes, maybe I said notation, so but before maybe I need to give the definition of the inverse function. So definition, the f, if f is a function from the domain to the range, okay, which is f of d f is one-to-one. So we need a one-to-one function first. Okay, then the reciprocal, if then the reciprocal or inverse function that we denote f minus 1, that is defined from fd to takes its value in d or df, okay, df, okay, is the function that assigns, so the y assign f minus y, which is an x, okay, is such defined how it is defined. So the equality, how we it is related to the original function, it is related by the relation by y is equal fx. Okay, so this is the relationship between the two. It's not any formula we are guessing, but it is connected directly to the original function. Okay, okay, so simple. Yes, that's all. Notation, we said f minus 1. Okay, okay. This is, yes, the important thing to know. There are remarks, maybe. Let's give a remark here. Yes, maybe instead of the notation here, I will put remarks here. Okay, so remark just to pay attention to some details here. You have, so if we have, so f minus 1, we said y is an fx. Okay, so will be x always. For any x you take it in the domain of f. Okay, now we have also f of f minus 1 of y will be a y. Okay, you start from the relation y equal fx. So f minus, yes, f minus 1, yes, f minus y is x and fx is y. So we will get y, and this is for any y in f of in the range. So you need to yes. Okay, so these are called constellation equation. Constellation equations. Just terminology, maybe you will. Okay, and like that. So these correspondence, these equivalence, allow us to find in some situation the formula of the inverse function. Okay, by finding an expression of f minus 1 at y. Okay, an example. So let's do one example. So so here is my function fx x3 plus 2. So plus 2. So is it 1 to 1? So first answer to that, then find f minus 1. Okay, so a way to find, so we don't have the graph now, but we can, it's a translation of the x3. We know x3 is the increasing function, so let's use the monotony. If I compute the derivative, I will get 3x2, which is positive. So my function f is increasing, then it is 1 to 1. Then f is 1 to 1. Okay. Now I need to find the formula for f minus 1. I know that f minus 1 of y equal x, equivalent to say that that fx equal y. That is x3 plus 2 equal y. So I need to express. So I need to find x with respect of y. So that's why I need to isolate x here. So I can write x3 is y minus 2. Okay. And from here we know that we can isolate x as square root cubic of y minus 2. And there is no restriction, everything is working. So finally, yes, I have my formula. It's this one. This is the relationship and define it for any y in R. Okay, so here is a way how to proceed. Yes, let's come back here now. Not notation. Let's correct here. There is a remark here on geometry on the graph. Okay, so if we have the point EB. So if I take EB, EFA, or yes, point A, here is FA. So this is, I call it B. So we have EB. Then F minus 1 of B is A. So the point B, f minus b, which is on the graph of f minus 1. Okay, so you have the point BE belongs to the graph of f minus 1. Okay, so here is B. So if this is my distance B, A is this one, so I can see it here. Here it is. So this is BE. the point B. And there's 2 points just by simple consideration, geometric consideration. They are symmetric. They are symmetric to with respect of the line y equal x. Okay. So the way a way to obtain the graph, to deduce the graph of f minus 1. So graph f minus 1 is deduced from the graph of f by symmetry with respect to the line, with respect of the line y equal x. Okay, so a way to do it, here it is. Sometimes it's harder to study function f minus 1, but somehow we know that our function, original function f, is invertible or has a reciprocal function. Then we can proceed like that. A last point, important point I want to address here is what about if my function f is differentiable? What can I say about f minus 1? So here is the following theorem, important theorem. Okay, so here it is. So we have the following theorem that says gives us answers. First gives us the fact if we have f 1 to 1 and f 1 to 1 and f continuous, then necessarily f minus 1 is continuous. Okay, punctually at a particular point. Okay, so we generalize on the small domains. The second theorem says if we have f 1 to 1 and f differentiable, okay, so let's specify now f differentiable at a particular point at A, and we need also to check that at so maybe let's say is differentiable everywhere or some interval, and we have or at differentiable let's put it at f minus 1 at A, and with f at f minus 1 at A different from 0. Okay, then we have that the inverse function is differentiable at A, and f, the derivative prime at A is exactly 1 over, is given by 1 over f prime at f minus 1 of A. So we can deduce, so you see, we can deduce the derivative, the formula of the derivative using the derivative of the original function f. The proof is very simple. It uses just the definition of limit of a derivative. Okay, so let's see one application. Okay, an example. What if I give you the function fx equal 2x plus cosine x, and you are asked to find f minus 1 prime at 1. Okay, what is it? The derivative computed. So if you see here this time, it's not easy. It's not even, maybe we cannot do it. You see, if you try to find the formula for f minus 1 for the reciprocal, we cannot isolate x. You have here a nonlinear equation. So it's not feasible. We cannot have an explicit formula, but still we will see we can compute the derivative at particular value of f. So first let's check the one-to-one property. One-to-one, is it one-to-one? So let's check, yes, derivability. Check the monotony, for example. I have 2 minus sine x, okay? So yes, it is always positive strictly. So f is strictly monotone, and then f is one-to-one. So we can say it is one-to-one. F is one-to-one. So f minus 1 is well defined. I will need, what is it, 1. 1 I wanted is an f of some a. So what value a that I can substitute here? 2a plus cosine a. Which a can I choose so that I get 1? Yes, since it is monotone, if I can find 1, it is the only one. So here I see a is necessarily equal 0. Okay, cosine 0 is 1. 2 times 0, 0. So it gives me a. Okay, so we have f0. So we have f1 is equal f0. So f minus 1 at 1 will be 0. This is the first thing we needed. Second thing, we need to compute the derivative. F prime, f prime at f minus 1 at 1. Okay, so we need to check that it is different from 0 so that we can apply this formula. So it is the derivative at 0. Now the derivative here, it is my derivative, it's 2 minus sine, so it's 2 minus sine x, and take x at 0, so which is 2, which is different from 0. Good. And now finally, I know that f minus 1 prime at 1 is 1 over f prime at f minus 1 at 1. Okay, which is 1 over f prime at 0, which is 1 over 2. And here it is, we answered to the question. We can be interested also to find the line tangent. Line tangent at a equal 1 to the graph of f minus 1. So we know that it will be 1 minus f minus 1 at 1 equal f minus 1, the slope, and x minus 1. So f minus 1, we saw it, this quantity is 0. Okay, this quantity we found it, it's 1 over 2. So okay, so the line is half x minus 1. Okay, so like that we can yes, we will define new functions like that using the inverse function. Okay.